And there we're recording. Okay. So greetings and evening, everybody. Again, Jason Archer from the planetarium. I guess we've all met before virtually, and you're here to learn about more about the universe. And we've done the night sky, which is how the sky moves in seasons and whatnot. And we've did a little tour of the planets in the solar system last time, and looking at what makes a planet and how our solar system is organized. Tonight, we're going to look at stars and nebulae, what they are, and how we know a bit about stars and the evolution of stars, stellar evolution. You could entitle this program the lifestyles of the stars, right? And so stars are born, they live, and they die. And what is that path? And it's fairly well understood. So that's what I'm going to present. And like with all my talks, I try to relate it to things you can find in the night sky to make it somewhat relevant. So we'll be going between the sky and what's where things are found in the sky to what's happening there. So perhaps if you go outside, you can refresh yourself. Oh, over here, this is happening in the night sky and whatnot. So here's the outline for tonight. Introduction we're going to talk about properties of stars. There's quite a few of them and they're quite involved, and I actually simplified this, I hope, for this presentation tonight. Types of stars. There's a lot of different types of stars. No one star is the same, although there is some organization there. Our sun, it's right next door. Why not look at it? And then how stars evolve, how they live, and then what happens when they die. And they can succumb quite a few different ways, and of course, hopefully, I have some time for questions. So that's my presentation. Does anybody want to say anything, or if there's new people, or introduce yourselves, or anything you want to comment before we get going? Now's your chance. Okay, great. Feel free to unmute yourself at any time. You can put stuff in the chat. I may grab it, be able to see it. I may not. It might be better just to speak up as we're going along here. And okay, so let's do that. And there's a little bit of music coming through, which I always do, so you should hopefully be able to hear that. So here we go. Whoa, stars are big blocks. No. So stars, hundreds of thousands of times farther away from us than planets are from us. You know, the nearest star other than our sun is so far away that the fastest spacecraft we could possibly build and built so far would take several tens of thousands of years to get there. And given all that, we're really curious and kind of ambitious species, right? We want to know what's going on out there. We want to know how these stars are born, how do they live out their lives, and how they die, and where do they come from. And because stars are in our galaxy are so far away, looking here at our night sky, brighten up the stars for you. To us, they appear as just mere pinpoints of light. And even the most powerful telescope is only going to see a star as a mere pinpoint of light. Whether it be a ground or space-based telescope. And aside from our sun, right? So they're much too far away to, let's say, figure out their diameter. And we have to come up clever ways to figure out how big they are, how far away they are, how bright they are, how hot they are, how old are they, what's their temperature. So we're going to look at that. We're going to look at some familiar shapes too, and some stars that you may have heard of before. And perhaps on your screen here, you're seeing a familiar picture in the night sky. You're seeing Orion the Hunter here, and the three belt stars, shoulder, shoulder, and knee here, that make up Orion. There's the belt there. And we're going to look at some of the stars in there. And the stars that make up Orion are there's quite a bit there. So let's look at this star here. We're going to look at that. Perhaps on your screen, you might notice it's got kind of a reddish color to it. This is a Betelgeuse. It's a red supergiant star, 500 light years away. How do we know that? Betelgeuse, roughly translated, means armpit of the mighty one. Most star names come from the Arabic. You certainly hope that Orion here uses some sort of deodorant product, right? Armpit of the Mighty One. That's my humor. You know about my humor. It's why I don't have a lot of friends. But this star is estimated between some 9 and 10 million years old. And contrast it to our sun, our sun is 500 million years old. And yet our sun is middle-aged, while Betelgeuse is nearing the end of its life, and it's only 9 or 10 million years old. So why is that? Well, it turns out it's a supermassive giant star, and they burn their material. They burn much more brightly and use up their energy much quicker. You know, the hotter you burn, the shorter you live. That's Betelgeuse. How about this star right here? We couldn't, this is Rigel here in the knee of Orion, or the foot of Orion, depending on how we look at it. The surface temperature of this star is about 21,000 degrees, and we certainly couldn't live anywhere near this star. Okay, that's in contrast to our sun's 10,000 degrees Fahrenheit. That's quite a difference. Okay, Rigel's a blue supergiant red star. Betelgeuse is a red supergiant star. And this star is entering the later part of its life as well. It's 8 million years old, and it's used up, we know, most of its hydrogen, and that's its fuel. That star's fuel is hydrogen. Okay, someday that star will explode, and it will do so in what's called a supernova. We're going to look at that. Okay, of course, I showed you this. This is Orion, one of the first and original 48 constellations, cataloged by the Greek astronomer Ptolemy in the 2nd century. Yay, I hope I'm remembered that far away. And there you go. What else is in the sky? Well, if you take the belt and you extend it on down to your next brightest star, to be sure this isn't the brightest astronomical object visible from Earth. And that's an important distinction, that the sun and the moon is much brighter, and so is Venus and Jupiter. They'll all appear much more brighter in the sky. So do Mercury and Mars, depending on where they are in the orbit. Okay, but this is the brightest star in the nighttime sky, and this is the star Sirius. It's about twice as bright as the next brighter star, Canopus. Sirius is significantly larger than our sun, twice as massive, and shines much more luminous. And it's only 8.5 or so light years from us. In astronomy terms, that's like a stone throws away. That's Sirius. If you head the other way, does it do it? Oh, here we go. I should point it. I hit the wrong button there. Take the belt and head up the other direction on your screen there. You'll hit to Aldebaran and a cluster of stars over here. Aldebaran is also a huge star. This star, 30, 40 times more massive than our sun. If Aldebaran replaced our sun, its surface would extend out into the orbit of Mercury. Huge. Okay. Just next door, let's see, is this small grouping right here known as the Pleiades. Easy to find. It's kind of a staple of the winter sky, and Pleiades never really fails to impress. And what you're seeing at the corner of your screen here is a cluster of stars, what we call an open cluster of stars, perhaps 1,000, maybe 3,000 stars. Many of the stars here are failed stars that we call brown dwarfs. A handful of those stars within it are actually bright enough for us to see. They used to use this cluster to figure out how good your eyesight was. Most people could see 5 or 6 stars. These stars are all gravitationally bound together, moving through space as kind of one cohesive group. How did that happen? And they're about 400 light years away. It's right above the constellation of Taurus, the bull. Let's move to the north here. There's the north. We've got the Big Dipper right over here, looking to the north. We've got Polaris, the North Star, the Pole Star. Actually, it's a triple star system. There's 3 stars there. We see it as a single point of light, but there's 3 stars orbiting around a common center of mass. 400 something light years away, usually the misconception is that this is the brightest star in the nighttime sky, but it's actually the 50th brightest star. But Polaris is a yellow supergiant star shining with a luminosity of over 2,000 of our suns. And yet it's pretty dim in our sky. Why is that? Okay. We'll turn to back to the south here. So stars, I've identified some familiar stars that you probably heard of. And stars have properties. And the properties we'll break down for you are basically the star's size, its mass, its brightness, which we could look at 2 ways, how bright it appears to us and how bright it actually is. That's called magnitude, and then luminosity. The color of stars. Stars do have color. The surface temperature of a star, its composition, what it's made of, and how old is the star. And I've just thrown out a bunch of numbers for some stars to kind of get you an idea. Okay, so to do this, to figure out all these principles or these properties of stars, we have to figure out the distance to stars. All right? And once we find the distance, we can figure out a lot of these other properties. So distance measurements are critical to understanding these, what we call stellar properties. I'll throw up some labels here, and we're going to look at a bunch of these stars here that I'm labeling on the screen. We're going to kind of study them in a little bit more detail. And you see we kind of label them, their position in the sky, right ascension and declination. We talked about that, I think, in the first class. Its distance we measure here in light years, but there's another way we can do that. An absolute magnitude and an apparent magnitude. And we're going to look at that too. That's a brightness, 2 different measures of brightness of Betelgeuse, Rigel. In fact, all stars have these. I've just identified some of the highlights here. So I mentioned that distance is most important to us. So how do we measure distances in space? Well, we identified, I think last week, the astronomical unit. We also have the light year, and we have the parsec. The light year is the average distance, we said this last week, between the sun and the earth, and it's about 93 million miles. An alternative unit to that is the light year. Okay, and we use light years, writers use light years, science fiction uses light years and whatnot. It's actually rarely used in astronomy. We use it here in the planetarium because it's easier, it's kind of our brains can wrap around it. A light year is basically the distance traveled by light in 1 year, and it's equivalent to about 6 trillion miles. We can't grab that number. It's hard for us to process. Now, the other one is what's called a parsec. That's a little bit more complicated, and it has to do with some geometry. We're not going to get fancy into it, but that's how we measure distances, is parsecs. Okay, a parsec is a unit of distance, and it's equal to about 19 trillion miles. And it's actually closely related to how we go about the business of figuring out the size of the universe. So that's why we use what's called a parsec. Okay, so why are these distances important? And I said before, their distance, if we can figure out the distance to an object, like we did with planets, we can figure out the total energy, luminosity, the mass of the object. We can do that through orbital motions, right? The motion of the object through space in general, the physical size of an object. Now, the problem is distances in space are pretty far. And how do we do that? How do we reach and measure something that's beyond our reach? Well, to find the distances to the nearest stars, astronomers use a method called triangulation. Here's a great little example of it. If you extend your finger out, close one eye, and then open the other eye, you'll see that the object in the background will appear to shift its position from one eye to the other. What this is called is parallax. Trigonometric parallax is used to measure the distance to nearby stars. And this is how we do it. And you can try it for yourself again. Hold a finger out in front of your face, focus on something at a distance, close one eye first, then the other. As you alternate the eyes, you'll notice the finger appears to dance back and forth, or the object behind it appears to dance back and forth. This is, of course, an optical illusion. Your finger really isn't moving. but your eye sees your finger at a slightly different angle. So your finger's location relative to the stuff in the background just looks different. And this shift we call parallax, okay? And if you measure the angle at which your finger appears to move, you can figure out how far your finger is from your face. That's how we measure stars. Let me give you a star picture reference though for it. So how far to the stars? So what we use is we use the Earth's orbit around the sun. And we use, here's the Earth and here's the sun, and we use that as what we call a baseline. Okay? We need a big one. Stuff are far away. So our baseline is the entire one orbit, or half an orbit, I guess you will, of the sun, or the Earth around the sun. 93 million miles, 93 million miles. That gives us our baseline. So we'll measure a star against the background of the other stars. Okay, and what's going to happen is the stars are going to appear to move. So if we measure a star at one point, let me get rid of this. If we measure a star, there we go, over here, where it is in the sky against the background of other stars, and then 6 months later, we measure it again against the background of the stars will seem to move, they actually seem to move in small little ovals. We can record that. We know this here. We're going to know this angular change here. Let's see this here. And we can actually figure out the distance. Now, angular, I said angular because what you got to think is the sky is a sphere, right? And we actually measure things in angles, right? So the baseline is the Earth. It's going to be 150 million miles or so, right? Okay, we observe a star in December, and then we say we observe it 6 months later. Okay, we get another position. Okay, and what we're actually measuring is an angle of that change, and we do it in arc seconds or arc minutes. And I just put this up here to say if you take the whole sky and you think of it as a sphere, which we do, right? You know there's 360 degrees in one circle, and then you take each degree and you break it into 60 segments, and that's an arc minute. Then you take each arc minute and you break it down into 60 more increments, and that's an arc second. And that's how fine detailed we can get. And that's what we do on the sky. There we go. So then we look at that star again in June, as we've gone halfway around the orbit. So we're looking at a star from two locations around the Earth. And if the star is reasonably close, they're going to appear to change position, and we're going to get an angle out of that. Okay, and we can use that, adds a little bit of trigonometry and a parallax angle, and we're not going to bore you with that, but we can actually get you a distance to that star, and that's how we do it. And that's what parallax is. I'll show you another image here. So the definition of a parsec then, this is a tough one, but well, maybe not. Okay, so why a parsec? Well, here it is. 1 parsec is a distance to an object whose parallax angle is just 1 arc second. And, so again, parallax angle, 1 arc second. And astronomers like that because it just makes the math a lot easier. Okay, so there's a parallax angle of 1 arc second. Okay, so if a star is 1 arc second away, it's 1 parsec away. And this is because this is how we measure distances, is with using parallax. All right. 1 parsec is equivalent to over 200,000 astronomical units. It's 3.26 light years and whatnot. Okay, so for astronomers, that's what works. So that's how we get distance. The takeaway is that stars that are closer have larger parallax angles than stars that are farther away. Makes sense. There's limitations though. Stars that are very, 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 very far away, which a lot of them are, that parallax angle can be too small to actually measure accurately. So in general, the greater the distance, the smaller the parallax, so the less precise the distance measurement will be. Give you a little demo here, get rid of all these graphs here. I'll give you a little demo here. So here we have the Earth. And here we have a star we're looking at. And this is the star's position change against the background of the stars. And there's your parallax angle right there. And in that, we can get a distance. Pretty cool, huh? And doing this, we've been able to measure, whoopsie, remove that. Oh yeah, here's a collection of stars showing, remember I said they're circles they make on the sky? So what you're seeing here is a result of the Earth's orbit and that change in the position of the stars. So you can see Sirius makes a really big change in its position, and it is closer than Procyon here, right? So that shows you the farther away you are, the smaller the parallax angle you're going to get. Some stars are so far away that we can't measure their motion. So some of the nearest known stars are, here you go, kind of give you an idea of distances out there, where they are from the sun. And most of these stars, like I said, are too dim to see without a telescope. So that's distance. And from that, now we can answer a bunch of other questions. We can answer brightness. Just looking on your screen, you can kind of tell which stars are brighter than other stars. There's two ways we measure brightness as to stars. We can do its luminosity, okay? And that's the total energy output of a star. We can also, and it's independent of how far away the star is, okay? We can also do the star's apparent brightness. And that's how bright the star appears to be from a distance, okay? And that apparent brightness depends on how far the star is from us. Two ways, okay? And here you go. There's some math. We measure luminosity in watts, in apparent. I'm going to worry about that too much. Remember, I'm going to kind of skip over this, but there's a relationship between distance and brightness too. You move 2 times closer to a light source, it'll appear 4 times brighter. No, we're not going to go there. But anyways, so let's look at the apparent brightness of some stars here. This might help, or not. Oh, okay. So again, how bright it is in physically, luminosity, and how far away it is, distance, okay? And appearances can be deceiving. So just because we look on the screen here and we see the stars really bright, is it just intrinsically very luminous, right? Or is it intrinsically faint but located very nearby, right? So to know for sure, you must either know the distance to the star or some other distance independent property of the star that clues you in, right? So what do we have? We have kind of 2 ways to look at it. We have what's called a magnitude system, okay? It was developed, the system to measure brightness stars is still developed back in Hipparchus, back in 300 BC. And he ranked star magnitudes from first, second bright, first, second, third, and so on and so forth. First being the brightest stars, and second magnitude being the second brightest stars. All right. The faintest stars visible to just your eye are like 6 magnitude. And that worked back in 300 BC. But now, once we are able to measure these brightnesses better and kind of break it down more, we had to change, well, not change, we didn't change it, we had to expand the magnitude system. So what we thought was the most bright, 0, turned out not to be. And so we didn't have to change the entire scale system. What we did is we just modified it and said, well, okay, Venus is much brighter than Vega, the bright star Vega, and Sirius. So we're just going to go into the negative. So the more negative a number is, the brighter it is. Okay, and that's why the sun is out here at like a minus, I don't know, 27 or something like that. Okay, so this it's kind of weird, but that's how we do it. And each change in magnitude number is let's see, 5 steps. No, 5 steps of magnitude factors in a factor of 100 difference in brightness. Yeah, all right. So that's magnitude. Now, oh, come on. So that's apparent magnitude. Now, that's how bright the apparent magnitude, how bright the object is to us. But absolute magnitude, how intrinsically luminous it is, well, to do that, what we do is we take all the stars and we put them at a distance of 10 parsecs. There's that parsec thing again. All right. And we reside them all together, put them all together. Imagine we could do that. And then we can compare them. So when you look at absolute magnitude, that's how they compare to one another, the same distance away. So that's a measure of how bright the star actually is. Okay. And it depends upon the star itself, not how far away the star might be. So here you can see the big M is the absolute magnitude, the little m is the apparent. And let's see here. Well, look at this star. Betelgeuse here is almost 500 light years away, and its apparent magnitude is -5. This star is only 66 light years away. Aldebaran, which appears to be about the same brightness when we look at it, actually almost is, but in reality, it's actually a much dimmer star. It's not putting out as much energy. Okay. This star, Rigel, is a almost 7 compared to a -5. It's intrinsically more brighter, but look how, and it must be much, much brighter, and it's much farther away. Isn't that crazy, huh? But it's so bright. Yeah. Okay. Gives you an idea. All right. So stars have brightness. They have a distance to them. Stars also move. And to the naked eye, stars appear fixed on the sky, but they actually move in reality. And what we call this is proper motion for proper. And there you go, proper motion. If we could watch the stars, there you go. You can see them moving there. So stars they'll move across our field of view or up our field of view. Stars can even move towards us or away from us, and that's a little bit different motion. But if a star appears to move across the sky, we call that a proper motion. All right. So this just shows you the motion of stars. Here we're going to put things back in order. The closer, the bigger the proper motion. It tends to be the bigger the proper motion, the closer the star. The smaller the amount of proper motion, the farther the star. Run that once again. There you go. Cool, huh? Okay. This was actually first noted by Edmund Halley back in 1718. He did it with Sirius, Aldebaran, and Arcturus. And he compared the positions recorded by Hipparchus back in 300 BC. So it took 2,000 years to get enough motion to be measured. Pretty crazy, huh? There we go. The other thing is, if a star is moving towards us or away from us, that's not proper motion, but it figures it would do this. It's called radial velocity. Sorry about this. Hold on a second. Let me see if I can find this. Doppler. It did this to me last time. The file is not found, and I don't know why. See if I can find the video here. It's basically the Doppler effect is what I want to show you. That's too bad. Hold on a second, guys. Let me see if I can find it. No, it's not there. Again. Basically, it's what I was going to show you is that stars that move towards us or away from us, if they're Doppler shifted, it's just like a siren coming at you, or you hear the pitch change. That's a Doppler effect. So if a star is moving towards us, it's shifted towards the blue end of the spectrum. If it's moving away, it's red shifted. If there's no shift at all, it's moving across their line of sight. Okay, and it just demonstrates the three motions that a star, space is three-dimensional, this way, that way, there you go. I'll have to figure out why that's video is not there. My computer's really being funky here. Hold on. Let me stop that. Hold on, everybody. There we go. Let me get rid of that. Here's just another demonstration of proper motion and all the proper motions of the stars on the sky here. And you're going to see the motion of these stars move. We're just going to demonstrate kind of real-time trails, the motion of stars in the sky. So we're moving forward 1 million years in 15 seconds. Wild, huh? Okay. All right, so let's come back to our starry sky. Color. If I oversaturate the stars, you'll probably notice that stars have color. They shine other than white. And have you ever wondered why they have colors? And what colors do you see? I've oversaturated the stars here to see that stars are red and white and blue. And there's some orangey ones here. I don't know how well they come through on your screen. There you go. That's a better view. Stars come colors for different reasons, 2 different reasons. Basically, temperature. The redder stars are cooler stars. Warmer ones are orange through yellow and white, and the hottest stars are blue-white. The color of stars also tells us something about the star's relative age. Luminous stars could be red or blue, though, and dim stars, though, however, are generally red. Now, it also tells us a little bit about what stars are made of, and you'd be surprised to know that stars are made of the same stuff as the rest of the universe, mostly hydrogen and helium, and then there's other elements. And except for a few differences, most stars are pretty much made of the same different stuff, okay? But why do stars then have different temperatures? We'll get to that. Stars have masses, and we do that like we measured the mass of planets before. We can use Kepler's laws and whatnot to figure out the weight. And basically what we do is we look for the orbital motions of stars. Well, how do we do that? Well, most stars in the night sky are multiple stars bound together. So actually more than 4/5 of the single points of light that we observe are actually 2 or more stars orbiting each other. Okay, so multiple star systems are binary stars, systems of only 2 stars. We've got a bunch of different types of binaries. We can have visual, spectroscopic, eclipsing, and astrometric binaries. Depends on how we kind of observe them and whatnot. So using this, we can kind of figure out a lot about the stars. So Sirius here, the brightest star in the nighttime sky, is a visual binary. And they have a wide enough separation to them that they can actually see them through a telescope. Okay, and if we can do that, we can figure out, using some simple math, their masses. There's an image. This is the double star system in Canis Major. Okay. Okay, this is actually Sirius here. Right? So you've got one star here, another star here, and they're gravitationally bound, and we can see them And because we can see them, then we can measure them and we can figure out the masses. If we can't see them visually, they're too close, even through a telescope, we can use it spectroscopically. It's called the spectroscopic binary. And we just measure the wavelengths we get from the stars to determine their orbits and then their mass, ZIZ. Like Alcor and Mizar and the handle of the Big Dipper, an example of that. There's Alcor and Mizar right there, okay? And we can spectroscopically look at it. Now, what you saw were like two stars there, but Mizar itself, let me get rid of this, hold on a second. Mizar is the brighter of the two. Mizar itself is a binary star. Okay, so it's a quadruple star system. Okay, and we can only see that by looking at it spectroscopically, is my point. So then using that, we can actually figure out the masses of these stars and their orbital properties. Another type is an eclipsing, and they orbit close enough in such a way that one star passes in front of the other as viewed here from Earth. And Algol is a good example of that. Hopefully this video works. I fixed this one last. It does, good. And if we're in the right line of sight, we can measure the brightness over time and the dip in the light from one to the other as they orbit each other and figure out mass from there. Okay. So that's ways in which we figure out the masses of stars. Once we get all this stuff, we can put all this together. When we've been studying stars, astronomers found that we can organize all these stars into one graph. Okay, let me fix this for you. It's called the HR diagram, and it takes all stars and it puts them in one picture, takes the masses and their brightnesses and lays them out. It's called the HR diagram, and it is the key tool in tracing the evolution of stars. And we got brightness, luminosity on one side, and what we call spectral class on the other side. Okay. So stars actually begin their life on what's called the main sequence, and that's what we're building here. Okay. Then they evolve off into the red giant phase and supergiant phase before dying and then moving into becoming a white dwarf at their endpoint. And all stars follow this path. And the lifespan of the star can be figured out depending on where we find the star on this, what we call HR diagram. They spend most of their time here, okay? And less time is giants and super red giants here, up here, you know, Betelgeuse and Deneb and whatnot here. It's harder to see on the screen here. I had to make it full screen for you to see. See how much more we got here. And then they'll be here and they move off to here and then they'll become a white dwarf over here. Okay, so by measuring the luminosity, figuring out the star's temperature, we can put it into a spectral class. Okay, we can put the star on this chart here, this graph, and we can figure out where it is in its lifespan. And based on that, we can figure out the lifespan of the star, where it is, and how long it's going to live for. Okay. The big takeaway for all this is that low mass stars generally are not that bright and don't have high temperatures, but they live a long, long time. Whereas high mass stars, they burn really bright. They're going to be really hot, but they're not going to live very long. So with that in mind, let's just look at some comparisons of sizes. So we're going to reset this. And I've showed this before with the planets, but we'll show this again here with the stars. We're going to add the stars and just do a size comparison to give you an idea of the sizes that stars have. Nice visual representation, if you will. So it's going to start with the planets and the moon. While I was doing that, I'm just going to grab a bit of water here. So I'm going to let this play. Hold on. So I got the planets here and a bunch of the moons. Actually, no, all moons. I haven't gotten the planets yet. There we go. Now we're adding some planets. I was going to cut this down, but I figured it just helps us kind of figure out the sizes here. All right, now we're getting to the stars. So there's the sun. And let's add some of the other stars that we might look at, just to give you a nice little size comparison here. So on the smaller end of the scale, Proxima Centauri, the closest star to us, is actually barely a star. And then there's things called dwarf stars, brown dwarf stars, which are almost like Pluto or Jupiter in size. Sorry, brain. On the other end of the spectrum, we'll move the other way. Sirius is over here, Sirius. Pollux, almost 10 times the diameter of our sun. Arcturus. Aldebaran, mentioned that one in Taurus the Bull. Rigel in Orion. Now we move out from here. Which star we got here? This is, oh, that's Antares. And we get to Betelgeuse, 1,000 times the diameter of our sun. And we get some of the biggest stars we know of, like Canis Majoris and UY Scuti, 1,800 times the size of our sun. Okay, so wow, really big stars. Okay, give you an idea. All right. So we've looked at the properties of stars, learned some interesting relations between temperature and luminosity and mass and all that stuff. HR diagram, which you could do a whole class on that. But let's look at our sun, our sun, and closer look at it. And then let's look at some other stars out there too, and in different stars in different stages of evolution. So what is a star? I don't think I mentioned that. A star is a self-luminous celestial body consisting of, everybody says hot gas, but it's plasma, which is an ionized hydrogen. And what holds it together? Gravity, lots of it. Okay. And their temperatures range from millions of degrees within their core, and the temperature changes as you get out near the surface of the sun, and then changes again as you get up into the atmosphere. Now, most of what is known about stars comes from studying the star closest to us, the sun. It's 93 million miles away. It's a few 100,000 times closer to us than any other star out there. So we know a lot about it. And our sun is average, middle-aged. Average depends on how you want to think about our sun. Compared to nearby stars, the sun is pretty luminous, hot, and big, right? It's the biggest star out there to us. But compared to the compared to other stars, apparently bright stars, the sun is actually dim, small, and cool. Compared to stars that are really, really old, our sun is really, really young. And compared to stars and things called open clusters, our star is actually very old. By definition, it's a G2 type main sequence star, and it's been shining for about 5 billion years. How could something that massive live for so long?
Yeah.
Well, nuclear fusion is now known as a source powering our sun. It's true in other stars too. This is actually a recent discovery, okay, of what powers stars. It's nuclear fusion. It's that simple. It's taking hydrogen and forming here. It's taking hydrogen, then making helium, then eventually it's going to try to burn other stuff, but it's burning hydrogen. Most of the universe is hydrogen. To scale, well, we already looked at this. Another picture of the scale of our sun compared to the Earth. There you go. We can look inside the sun. There we go. Sun has layers to it, much like the cores of planets do too, right? And I already said that most of the sun is hydrogen, and then helium, and then believe it or not, there's oxygen and carbon and iron and some other elements. Any element that is heavier than helium is considered a metal atom and a heavy atom. So oxygen is considered a metal. Interesting, huh? Our sun currently fuses something on the order of 600 million tons of hydrogen into helium every second, converting 4 million tons of matter into energy every second as a result. And this energy that's been created takes anywhere from 10,000 to 170,000 years to escape from the core and out to the surface of the sun. This is a big thing. There are layers to the sun. There's your layers. It has a core, the innermost part of the sun. It's where the nuclear fusion is occurring. Tremendous amount of gravity in there, creating that ability for helium to be fused. It takes a lot of energy to do that. Extremely high temperatures to do that. So in the core, you're looking at 27 million degrees. And then out from there, you've got a bunch of different zones, like the radiated zones. And that's where the energy is transported from the interior to the colder outer layers. Okay. Then from there is convective zone, and we're getting progressively cooler. And now it's gas transporting the energy, kind of like the top boiling pot of water. The gas coming up, hot gas rising and then cooling, rising and then cooling. On that surface, we can actually photograph it. So we call it the photosphere, and it's visible to us. And we've gone from 27 million degrees to 10,000 degrees on the surface. Okay. And if you look close to on the surface, you'd see granulation. There's the top of that boiling pot of water there. And you're seeing where it's very bright, gas is coming up, and where it's darker, gas is descending. It only looks dark because it's cooler than where the gas comes up, so it looks darker. We call this granulation. Kind of think of the surface of the sun as bubbling. There's also things called sunspots on the surface of the sun, and the sun's a big magnet, and where those magnetic field lines pop out of the sun and back in, it actually cools it's a cool spot on the surface sun. So we call them sunspots. Sunspots are important because it has to do with how active the star is. The more sunspots are, the more active the sun is. There's actually a pattern. And they've found correlation of the number of sunspots to ice ages here on Earth. So there is a correlation between the amount of energy and how active the sun is and what happens here climate-wise on the planet. And we're still figuring that out. These spots are huge. There you go. They're big. Very, very big. Above that, we have an atmosphere. There's actually a couple layers, what we call. There's a chromosphere. Okay, it's just above the photosphere. Temperature is where the temperature starts to rise again. Okay. And it gets up into the millions of degrees here. Okay. And it all has to do basically with the temperature of the molecules that are there. Okay. So you've got outside the chromosphere. Oh, there's the chromosphere.
Yeah.
You got to block out the photosphere to see it. Okay.
He didn't finish yet.
I'm sorry? And then there's the corona. And that's the outermost atmosphere. And here, like I said, it gets up to 2 million degrees. This is where the solar wind begins. And we can only see these layers during eclipses. Okay. So what can we see up here? Well, oh, and also note, just because it's 2 million degrees, there's high temperature, but there's not a lot of heat. Okay, because there's not a lot out here. There's not a lot of molecules, okay? So you can have a lot of, remember, temperature's a measure of how fast molecules are moving. Heat is heat is more what it feels like. And if we were to put our hand there, it would be freezing, but the molecules are moving pretty fast out there. So that's why the temperature is so high. There's things called prominences and flares and whatnot that we can find up in the corona here. This large, bright gaseous feature extends out from the surface, and it kind of, these prominences, they're looped out of the photosphere, they're anchored to the photosphere, but they extend outwards into the solar corona. Okay, these giant gaseous features, right? Now the sun also has a solar wind, and you've got fast-moving ions that escape the sun's gravitational attraction, and they move outwards at hundreds of miles per second. Okay, and this is the solar wind, right? And our atmosphere is hit by this stuff, and we'll get there in a minute. Sometimes you get these solar flares, and it's where these magnetic field lines coming from the sun will kind of snap and release a bunch of energy out. A sudden explosion of energy is called a solar flare. Lots of radiation is released into space, and it can actually interfere with communications and whatnot, satellites here on Earth. We have to keep an eye on, cause brownouts. Sometimes they're accompanied by what's called coronal mass ejections, and there are huge bubbles of radiation and particles from the sun, and they explode from the into space at very, very high speeds. And thankfully, you've got this solar wind coming out. Thankfully, we have a magnetosphere that actually helps protect us from this harmful radiation that's being shot out from the sun. We're being protected by it. All right, and it's this, our magnetic field and interaction with the sun's energy here that comes out that causes auroras there. All right, give you an idea of an aurora here. Actually able to get it. I didn't get this, but it should play in a moment here, or not. Hold on a second, everybody. Why is this not playing? Stop that again. I wanted to show you time lapse of an aurora. It doesn't seem to want to do it. Well, it's not doing it. Let me try one more thing. There you go. That's what I wanted to do. There's your aurora there. And so you're seeing an interaction of these solar storms from the sun interacting with Earth's atmosphere. By the way, they're very hard to photograph and capture. I do have a colleague that's gone out to do this, and he had it's cold, it's freezing, it's dark. He had a bear of a time to try to get it. You got to get the timing just right, right? Let's head back to the sun here. So I think I said that it's nuclear fusion, and the sun produces a lot of light every second, and it's been doing that for billions of years. And this tremendous amount of energy is nuclear fusion. The specific kind of fusion is called the proton-proton chain. And I don't even know if I could go into a full detail. It's been so long, but it's how stars like our sun combine hydrogen together. And it's a multi-step process is all you need to know, right? And in that process, energy is released, helium nuclei are created, at the same time, okay? And bigger stars have a little bit more complicated process, but it's the same idea to creating energy. And realize that to do this, you need incredible amount of gravity. And the reason a star, you'd think, well, if a star is that massive, why doesn't it just collapse in on itself? Well, as soon as a nuclear reaction happens, you get pressure outward that balances the gravity compressing inward. And that's called hydrostatic equilibrium. And that's what keeps the star in balance. So gravity wants to pull the star in, and the pressure wants to push the star out from the nuclear reaction. As long as the star is in hydrostatic equilibrium, it's going to be on that main sequence, and it's going to be balanced, and everything's going to be fine. The star is neither going to expand nor expand, or contract or expand. Once that gets out of balance, then we're going to start to have problems. So where does this all happen? Where does nuclear fusion start? Where does it begin? Well, it begins in space. Yeah. Yes, but a little bit more specific than that. Well, stars form in nebulae. Okay. We'll measure lifetime of stars in millions of years, right? Billions of years. And they start in what's called nebula, in a gas cloud. Within that cloud, you'll get a protostar. Then you'll get the onset of hydrostatic equilibrium. You'll get ignition of a core of hydrogen burning. You'll get thermal equilibrium, and then you get a star. And they all form in what's called these H2 or molecular cloud regions that you see here. Okay. These are nebulae. Giant gas cloud of molecules. And they're shown here. I'm showing you here. They're mainly in the disk of our galaxy here. That's what you're seeing here in the blue there. Another way to think of them is they're stellar nurseries. We also call them H2 regions for hydrogen because that's what we need, right? Makes sense. They're generally found in the plane of our galaxy, but not always, but most part. All right. So some examples of these. There's one there. Stars are being born in this area right here. Or how about this cloud right here? This is Rho Ophiuchus. Right here. And this is a giant molecular cloud complex, they call it. It's gorgeous. It's one of the oldest stellar nurseries to the solar system, very well photographed, and it's where stars are being born. You can see the nebulae there along the plane of the Milky Way here as we kind of spin around through space. So in our night sky, let's come back to our night sky. A great example of one is on Orion. It's right below the belt. It's M42, the Orion Nebulae. It's called the Orion Complex. It's about 1,300 light years away, okay? And it's several hundred light years across, and there's enough material in there that suns, tiny suns, are being formed as we speak. Okay. Cool thing about the planetarium is we have like cool volumetric views of it here, which I'll show you in a minute. There you go. There's a 3D volumetric view of this Orion Nebulae where stars are being formed. There's 4 stars in the middle there we call the trapezium, and they're energizing and heating all the gas that you see around there and causing gas and stuff, material to churn and coalesce and get together. Okay, that could be it. Or in some cases, you get a supernova, massive explosion of a star, and it sends kind of shock waves and causes gas clouds to compress, and that you get gravitational collapse. Excuse me. Either way, you're looking for the formation of protostars, something like that. And here you go. I forgot I had this image here. So what you're looking for is what's called a protostar. That star forms by definition when nuclear reaction occurs. You get that nuclear fusion and boom, the star is born. Yay! Actually have a picture of that here for you. There you go. This is from the ALMA telescope. It's a massive protostar that's been photographed, and this is ALMA's in the Atacama Desert in Chile. And it's a protocluster. It's in the Cat's Paw Nebula. If that means anything to you, but that's an image right there. I can actually take you into the Orion Nebula here. I hope this one works. Why is this not working? Now it's working. And show you what we think it might look like inside the Orion Nebula. Kind of fly through what's called the veil, and we descend through this kind of gaseous area here. You know, you've got winds and radiation from the central star kind of pushing material out of the way and making this valley. There's those bright stars there. So within here, you'll see these newborn stars, and around them you'll see planets might be forming around them. At least we think anyways. And again, this is just a simulation of what we think is happening inside the Orion Nebula. Who knows, maybe our solar system 4 billion years ago started in an area something like this. Get rid of that. Okay. A couple other examples. I'm going to show you one other example only because I like to do just one of each here, but people seem to know this image. Maybe they do. This is the Eagle Nebulae. It's in Serpens, which is there. It's a summer constellation. But there's the Eagle Nebula, 5.5 million-year-old gas cloud located right there. Notice it's in the Milky Way. I'll magnify it. Also very well photographed. You've got the colors here, they represent elements. So you've got blue colors that are hydrogen and or oxygen, and red is sulfur, green is nitrogen, and hydrogen. We colorize these things so we can see them. Anyways, oh yeah, I should be showing you the right image for my narrative here. There you go. So this is called the Pillars of Creation. And a lot of people have seen this picture, so I thought I'd show it. It's a Hubble image, and you're looking at an active star forming region within the nebulae where newborn stars in their kind of these wispy columns, right? And we have, here's some images of these newborn stars with these jets of gas extending out for them as they form. So young stars can form in clumps together. And remember that Orion Nebula, Pleiades that I showed you over here, that's M45 right there. Refresh where that is, up that way from the belt. So here's a group of stars, thousands of stars, 400 light years away, known as the Seven Sisters. If you own a Subaru, there it is. But this is an example of an open star cluster. Stars all born at the same time, same gigantic gas cloud. They're fairly young stars. All right. And the gas and stuff you're seeing could be either gas around the stars that were part of when they formed, or it's just passing through that. All right. So example of young stars. Of course, we have old stars too. And we can find one of these here in Hercules. And you're looking for M13. And it looks something like this. Now, this is a globular cluster. Looks kind of like a cotton ball through a telescope and shiny little flakes sparkling, kind of a snow globe. But you're looking at perhaps millions of stars there. This is 25,000 light years away. They're found on the outside the plane of the galaxy. Okay. And these are old stars. Okay. Called the globular cluster. Let me see if this will work. I do have another simulation of this. Let me see if this will work. It's doing something. And it's not doing anything. Oh, no, it's doing something. Oh, okay. It's going to show you the, no, that's not at all what I wanted. Move that. All right, well, a second visual that didn't work the way I wanted it to. Sorry about that. But these globular clusters, there you go. So these dots here, this is even better. Show you where they're found, these collections of really, really old stars. And they're estimated to be 10 billion years old, and they contain some of the oldest stars in the galaxy, and they're outside mostly the plane of our galaxy there. They likely formed very early, probably before our galaxy even spiraled into a flattened disk here. Coming back here. So we got old stars, we got young stars. We've got stars that almost, they're like not really stars, but they are stars because of how they formed. Below Orion here is Lepus. And in there is what's called a brown dwarf. Now, brown dwarfs, they accumulate material like a star, but not like a planet. And they condense from a gassy cloud. They have a higher mass than planets, so they tend to have stronger gravity. So they can hold on to their lighter elements like hydrogen and helium. So they're more really stars, but they fail to collect enough material to become actual stars. They never create nuclear fusion. They never have that reaction. So we call them brown dwarfs. Okay, and they're kind of right in the middle between a planet and a star. Okay, and we think there's a lot of them out there. Okay, so brown dwarfs are not planets. So we think of them as failed stars. They're not as massive enough to power hydrogen fusion reactions. So they kind of get their own classification. This is an example of one. Gliese 229, the brown dwarf. We'll fly to it. That's the star, and next to it, oh no, that's the planet. I'm sorry. Yeah, they're the dwarf star. Brain. So there's the star, and there's the brown dwarf right there, next to it. This is one of the first known brown dwarfs around the star Gliese 229. So hence 229b. That's the planet. So young stars, old stars. Let's come back to our sun. And I've got, well, it's a somewhat short version. It should all go away. Let me see how long this is. Okay, so about 5 minutes here. This is the evolution of our sun. And what's going to happen to our sun. So we've seen stars that are really old and stars young. We've seen stars that haven't become, but our star is an average everyday star. So what's going to happen to it? Let's just let this play out. You know, there's enough hydrogen in our sun right now to keep the process going for billions of years. But eventually it's going to run out of almost all the hydrogen in the sun's core. It's going to run it out, and it will have to fuse helium together. And it's not going to be able to generate as much energy when it does that. And what's going to happen is the star is going to start to collapse under its own weight. Okay. And when it collapses under its own weight, it's not going to generate enough pressure to fuse helium as it did with hydrogen. It's harder to do. Okay. Now there's some hydrogen still left at this core. It's going to begin to fuse, and it's going to generate a little extra energy and keep the sun shining. Okay. Here's a outside view here. It's going to start to get really big. It's going to expand. Okay. And it's going to shrink back down again. It's going to go through this kind of expansion and contraction as it tries to burn heavier and heavier elements. It's going to turn into a red giant. And it's going to eventually get so unbalanced, it's going to puff off its outer atmosphere and blow this stuff off into space. It's going to form a nebula, actually. It'll do that a few times as it kind of progressively blows out its layers. And the core, what's going to be left over, will shrink into what's known as a white dwarf. You'll see that momentarily. You're seeing over here what it would look like from a distance away. And we're getting near the end here. It's, you know, through this process, it's trying to burn hydrogen, helium and oxygen and carbon, the result of burning all these other gases. And it's just not going to do it very well. The sun's going to get very out of balance. We'll probably be long gone by this point. It's going to take another, we're looking at this in 5 billion years. What's left over is what's called a planetary nebula with a white dwarf in the middle of it. Let's see if that comes up here. The simulation is much better on the dome, but it is what it is. There's your white dwarf. We have examples of what this looks like in the sky for real. It's just waiting to see. This is a new simulation I just got, and I just want to make sure it comes down and it shows you the nebulae. But I'm going to show you one anyways. Yeah, there you go. There's maybe what it might look like. But we have examples of this in the sky. So we know this. So let's say an alien were to look back upon our solar system billions and billions of years from now, you're going to see something like this here. So they might see something like this here where the sun used to exist. It's found in our night sky near Lyra the Harp. It's a summer constellation. The ring nebulae is found there. Now we're looking a couple thousand light years away, and that's what you see. And there you go. There's a planetary nebula, a white dwarf in the middle. That's likely what our sun solar system is going to look like. Whoop! They just, yeah. Well, I don't know what happened. Oh, I know what happened there. Hold on, guys. Sorry about that. If I've got two programs or two files overlapping each other, one's still running in the background, it'll take over what I'm currently trying to show. You don't need to know that. We'll bring that back. There we go. That shouldn't go away. Why do we call them planetary nebulae? Well, they look like planets through a telescope. That's why. Okay. And in the middle, here's your white dwarf. So this is the end of a sun like our star, a star like our sun. It's exhausted all its nuclear fuel. It's the very end. You get this white dwarf. It's got temperatures that are pretty hot. Okay. And over billions of years, it's just going to get cooler and cooler and cooler and cooler. Typical white dwarf is about half as massive as our sun, but yet only significantly a little bit bigger than our Earth. So think about that. Okay, it's still pretty hot, and that's because it's like the size of our Earth. It's compressed, anyways, and it's very dense, like 2,000 times as dense as the Earth itself. It's really dense. Okay, so this is an example of one. Let's look at this in 3D though. See how I'm doing on time here. Yeah, doing all right. There's an example. This is M57. There's three-dimensional view of it. Another example is this one here. Fly over to it, called the Cat's Eye Nebula. Depending on how the star ends its life and the material that's left over and the material that's there and whatnot, and how many times it kind of puffs off layer and you get different concentric rings and all that stuff. It's almost like a work of art. This is the Cat's Eye Nebula. This might be a double star system, and that might be why you have the shape you have. Here's a two-dimensional view of the Cat's Eye. Okay, but what about stars much larger than this? Let's look at Betelgeuse. Don't say it 3 times. 3 times. Okay. There's Betelgeuse there. Note that if we were to bring Betelgeuse back to our solar system, that's how big it would be. That orange blob there is, it would extend out into the size of Jupiter, orbit of Jupiter. This star, it's massive, right? We've already said that. It's, what did I say? How more? 1,400 more times larger than our sun. Well, when this one goes, it's going to really get out of balance really fast. And it's going to be a supernova, the biggest explosion that we have ever seen. It's kind of the last hurrah of a massive star, 8 to 50 times the mass of our sun. And it's not going to go nova. It's just going to go supernova. Isn't that super? Tremendous energy, tremendous heat pressure. And the stars are large enough that you just see a massive explosion. It collapses and there's a shock wave and it goes back out, right? Gravity basically wins out as the star cools. And there's so much gravity that that's what happens. And I don't know why there's a white box on your screen. There you go. Okay. So we have examples of this in the sky too. Supernova 1987. A in the Large Magellanic Clouds. It was spotted about 3 decades ago. Astronomers spotted one of the brightest exploding stars in over 400 years, and it's supernova called 1987A. Okay. And let me call this up for you. That's what I want right there. It is, there you go. And then the explosion itself is not, I hate computers. There it is. Ha, there it is. Let's get rid of that one. There you go. There's the explosion right there. This explosion occurred 160,000 years ago in the Large Magellanic Cloud. It's a dwarf galaxy. And so that explosion, traveling at 186,000 miles per second, finally reached Earth on February 23rd, 24th, 1987. There you go. Okay. So you're looking at a massive explosion, death of a star. And there you go. We can chronicle it, right? There's kind of a chronicle of the ring that you saw there, out there. So why do we care about these? Well, some good reasons. We are made of star dust, right? And that's a phrase that we use a lot. We have been forged from the death of stars. So supernovae are the mechanism by which the atoms created in stars are spread out through and released into space. So two, there's high radiation, and this is how life evolves. We believe that the supernova explosions flood our galaxy with high energy radiation that might have contributed to the mutation that drove life here on Earth. That means we're a mutation. Certainly feels like it some days, doesn't it? So there's evidence that a supernova triggered the formation of our solar system billions of years ago. So we want to understand these things, right? Now you can get a supernova, you can get a binary supernova too, because I said I only show this because most stars are multiple star systems, but you know, this can happen with one star's orbits the other, and at least one of those stars is Earth-sized white dwarfs. Now, what you're going to get is material being pulled off the other star, and you can get kaboom from the white dwarf as it pulls material off the star, and it kind of self-inflates itself or makes itself bigger, and you can get another explosion. And apparently the star doesn't want to show you that, because so it's going to leave the screen. It's only going to show you a little bit of it. That's another type of supernova. There's a couple type, and it occurs in binary star systems. And you know, most stars out there are binary multiple star systems, so think about that. What's left over is called a supernova remnant. Okay, and we have an example of those out there too. We're going to show you one in Cassiopeia, and the universe just disappeared. Okay, we'll try that again. There we go. There we go, Cassiopeia, and we're going to look for supernova remnant right here. And there's one right there. That's a supernova remnant. Another spot of a dying star. And the light from this star reached just a couple hundred years ago. This is Cassiopeia A. I just show you this one because it kind of shows you the evolution of this supernova that we think, right? Kind of 8 stills showing kind of an artist representation of what the supernova probably looked like. You know, we're looking at speeds of tens of millions of miles per hour. Wild. We have another one out there. There you go. So what's left over? Let's see. Why did I show you this one? You know, it's good I put the presentation together and I have no idea why I'm showing you this. Oh, now I do. Okay. So what's in the middle of that, right? So a white dwarf left over for our star, but what's left over is what's called a neutron star. And it's an ultra dense object. So you think of taking the mass of the sun and packing it into a space no, it's taking this, it's a city-size object, taking the size of the sun and packing it into a city-size object. That's a neutron star. They're wicked dense. The teaspoon would weigh 1 billion tons, assuming you could pick up a 1 billion-ton teaspoon. Start working out. The gravity on a neutron star is 2 billion times stronger than on Earth. They're wicked dense, wicked packed. Okay, so that's what you get when a massive star explodes, is a neutron star. And here's an image of one there, right there. So we know these things exist, right? They burn pretty hot and cool off. We can show you one here. Oh, this is what I wanted to show you too. Getting near the end here. If we go to, remember the Pleiades and Andromeda, Aldebaran over here, well, what you want to do is kind of go that way and then go to Taurus the bull here. There's no bull about that. What you're going to look at is M1. So on July 4th, in the year of 1054 AD, the Chinese astronomers, they noticed what's called a guest star. In that area right there, right here, in Taurus the bull. And this source, this bright star, was visible for like 23 days. It was 6 times as bright as our sun, Venus. Okay, and it was there for a long time. It was also observed by other cultures too. The Anasazi people of American Southwest, they viewed it too. And they just a guest star in 1054. And you can see their representation of that guest star there. And so this is a pictograph from New Mexico, and it's believed to depict that event. And that multi-spiked star there represents a supernova near a crescent moon. This might just significant, your handprint that it was an important event. So they did that, but they recorded it too. Let's magnify. There we go. That's what it looks like. So that's a Crab Nebula. And in the middle of this Crab Nebula is a neutron star, but it's a special kind of neutron star that we call a pulsar. So this wasn't until like the 1960s that astronomers detected an object that pulsated with very regular, this period of fractions of a second, very accurate, very high precision. And there's this kind of joke going around that, well, maybe we're picking up signals from extraterrestrial civilization. If there is if there are aliens out there, they're going to look at our planet. They're just going to keep going. That's what I would do. Do you know what we're doing to each other? But anyways, so they kind of coined these objects little green men, LGMs. In fact, they're neutron stars. They're rotating very rapidly, and their beam of energy, radiation, is actually directed. We can pick it up. And if it comes towards us, it's called a pulsar. That's all it is. Okay. It's a rotating neutron star. And they rotate at tremendous speeds. And think about this. If they rotate at tremendous speeds, they have to be very densely packed, because at the speed they rotate, they'd fly apart. But they don't. They stay together. Okay, so they're super dense objects. Kind of wish they were little green men, because then they could take me away off, it's a joke. Anyways, all right, so here's an image of one right there. That gives you an idea of a pulsar. All right, so neutron stars, pulsars, we're not done. And that's big stars. Betelgeuse is 1,000 times the size. What's 1,000 times the size of our sun? What about really massive stars that are 15, couple thousand times the size of stars? Well, there's stars like this one here in Canis Major, right? That one right there is a extreme red hypergiant, or a red supergiant star. It's huge. It's massive. Okay. It's 1,400 times that of our sun. Give you an idea. These are the most massive and most luminous stars in the universe. Okay. They emit energy at a very fast rate. They only live for a few million years. and they're going to burn up their energy real quick. And when they do, they're going to go supernova, right? Give you an idea, this star, this is an artist's conception of a red hypergiant star. Isn't that wild? It's a hot star. Okay. When this star goes, it's going to go into not a neutron star and not a pulsar, but it's going to collapse into a black hole. There's so much mass, it's going to collapse into a singularity. And Einstein's theory of general relativity predicted this. So all that mass is squeezed into an area of space the size of, I don't know, New York City. And that's where you can get a black hole from. One of the ways you can get a black hole. And if there happens to be a star in the area around it, or it's a multiple star system, well, that black hole is going to be evident by the material that it's pulling off its partner star. So there, one source of a black hole. All right. Let's go back to our night sky here. So we've looked at quite a few things here. We've looked at star forming regions, things called planetary nebulae, globular clusters. Those are in the, we looked at stellar supernova remnants, we've called. Where are those? Let's call those up. There's your supernova remnants there. Things called pulsars, which are actually scattered throughout the night sky, the purple there. Okay. There's a lot of things out there. All right. Give you an idea when you look out there. So there you go. There's your stellar evolution, nebulae, birth to death. And there you go. We've got time for a few questions. If you have them, thank you very much. You can just unmute yourself, or you can add it to the chat if you want.
Hi, I just had a question about how do they know like the age of the stars? Is it just a guess, or how do they figure that out?
It's not a guess. You can determine this age of a star by looking at that HR diagram and placing the star there based on its brightness and its temperature, and figure out where it is in its lifespan. And that kind of dictates how massive the star is, how brightly it burns. You can figure out how old the star is and its evolution. So that HR diagram is kind of our key to figuring out the age of a star based on its brightness, its temperature, its color, and that's how we do it.
Okay, thank you.
Mm-hmm.
And I did have another question about, you had mentioned the heat and temperature, that they're two different things.
Yeah. Well, it's just a measure. It's how we measure. It's semantics. Okay.
Okay.
Temperature is how fast a molecule moves. The faster a molecule moves, the higher the temperature.
Okay.
Okay. But heat is what we feel. So when that molecule hits you, the more the molecules that hit you, the hotter you're going to feel, right?
Right. Okay.
But if you've only got one molecule, even though if it's moving very, 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 very fast, you're not gonna heat up at all. Heat's what we feel.
Okay.
Temperature is a measurement of the energy of a molecule.
Okay. All right. Thank you.
Oh, you're welcome.
Jason, one of the things that I found interesting is that all of the matter all the different atoms that exist are created in the hearts of stars.
Yep.
And then blown out. And so there's the term that says we are star children, or made of the dust of the stars.
That is true.
And the age of the evolution of our universe, a lot of this matter that we exist, that we have, had to have been created a long time ago by some very large stars that blew up and spread the atoms out over a very large area, and they had to be doing it for a very long time. Is that something
Yeah.
you'll be talking about on the next session?
I'm going to talk about the age of the universe, the big stuff, galaxies. Yeah, I'll talk a little bit about that. Not so much a little bit more the big structure of the universe is what I'm going to talk about in the next presentation. Yeah,
Okay.
but not so much. That's kind of what I touched on today, was that when a star explodes in a supernova, it spreads its material that it's created in the burning of hydrogen and helium and whatnot, the byproduct of that. It spreads that material out into space and causes the creation of other stars and planets and perhaps life. So that's when we say we're star stuff. You know, all the stuff, the table that I'm on, the computer that I'm staring at, was all that material came from the death of stars. It was all formed there. It's got to come from somewhere, right? That's where it came from.
Okay, thank you.
You're welcome, sir. Any other questions?
Yes. It just ended now. No, it didn't yet. He didn't finish yet.
Was that a question? Okay, if there's no other questions, thank you guys very much. The next class is the 9th, I think. And it's on cosmology and galaxies and whatnot. So I thank you guys very much for your time, and I appreciate it.
Thank you, Jason, for putting this together.
You're quite welcome.
Thank you, Jason.
You're welcome.
Thank you. Have a good night.
You too.
Bye.
Good night. Thank you.